Welcome to the solutions to the circular and planetary motion problem set, problems number 6, 7, and 8. Problem 6, a 55-kilogram ice skater is moving at 4 meters per second when she grabs the loose end of a rope, the opposite end of which is tied to a pole. She then moves in a circle of radius 0.8 meters around the pole. Determine the force exerted by the horizontal rope on her arms and compare this force with her weight. Let's start with a free body diagram of the forces acting on the skater. And we have a rope that will draw attached to her hands here, going this direction. And so obviously one of the forces would be the tension in that rope, and we'll label that T. The other forces, of course, are her weight down, mg, and the normal force of the ground ice pushing back up on her, Fn. You can see that the dot over here represents the center of the circular path, that there's only one force in this problem keeping her traveling in the circle. So the force exerted by the horizontal rope on her arms is the tension in the rope, and that force is causing her to stay in the circle. We start with our Newton's second law statement, sigma F equals ma. Is she accelerating? The answer is yes. She's traveling in a circular path, so she's centripetally accelerating. We put a C, subscript C on our A. Next, as always, we summate the forces causing the mass to accelerate. And in this problem, there is only one force. The tension is causing her to centripetally accelerate. So T equals mv squared over r. We make our substitutions, 55 kilograms for the mass, 4 meters per second for the speed, which we need to remember to square, and divide by the radius of the circular path, 0.8. We calculate, and we get 1.10 to 3 digits times 10 to the third newtons. B asks us to compare this force with her weight. So the first thing we're going to, of course, do is to calculate her weight. W equals mg. 55 times 9.8 is 539 newtons. Whenever we make a comparison in physics, we never use words like less than, greater than. To do that comparison, we always do a mathematical comparison. So to make that comparison, we go ahead and take our tension in our rope, 1100 newtons, divide by her weight, 539 newtons. The newtons cancels, and we get a 2.04. What that means, of course, is that the tension is 2.04 times her weight. Okay, let's move on to number 7. We have a certain light truck can go around a flat curve having a radius of 150 meters with a maximum speed of 32 meters per second. With what maximum speed can it go around a curve having a radius of 75 meters? Let's start by doing a free body diagram for this awesome Chevy truck that's over here in this picture, going around this curve on a freeway. Of course, we have the weight down of the truck, mg. We have the normal force, Fn, of the ground pushing back up against the truck. And we have some force keeping it traveling in the circular path pointed towards the center of the circle. Well, of course, in this case, that force would be the static friction between the tires and the road. So what we start out with finding here is what friction is required in the first circumstance with a radius of 150 meters and a 32 meters per second. We start off with, again, our Newton's second law statement, sigma F equals ma. Is the truck accelerating? Yes, because it's traveling in a circular path, so we add the subscript C to our A. What force is causing the mass to centripetally accelerate? As we just discussed, that force is the static friction, which is equal to mv squared over r. We have m times 32 squared over 150. And what we get is an expression for our friction in terms of the mass. 32 squared divided by 150 is 6.83. So the static friction is m times 6.83. The reason we're doing this is because that same friction, if it's the maximum value, is the same friction that's applying the centripetal force in the next set of circumstances, where we reduce the radius of the circular path to 75 meters. So we start again with our Fs causing our mv squared over r. What we're going to do is we're going to take our previous value of m times 6.83 and substitute it for Fs. On the right-hand side, we have the same mass, same truck, v squared over the new radius, which is 75. You can see that the mass cancels, which allows us to solve for the new speed, which would be 22.6 meters per second. This should make sense that you cannot go as fast in a turn of smaller radius when the same amount of friction is applied. It's the same truck, it would be the same normal force, the same coefficient, so mu s Fn is not going to change. Therefore, the Fs supplying the centripetal force to keep it traveling in a circular path is not going to change. So what needs to change is the speed, the max speed at which you can round that curve. All right, lastly, we go to number 8. We have a 50-kilogram child stands on the rim of a merry-go-round of radius 2 meters, rotating with an angular speed of 3 radians per second. We would like to know the child's centripetal acceleration. So that's AC. The minimum force between her feet and the floor. That sounds like the static friction that is required to keep her in the circular path. And then the minimum coefficient of static friction that's required, that would be mu s. Is the answer we found reasonable? And we're going to use that answer to determine whether it's likely that she stays on the merry-go-round or not. We're going to start with a free body diagram of the forces acting on this girl. We're shown here that the rotation is this direction. We, of course, have her weight down, the normal force of the surface pushing back up on her, and the static friction that holds her in the circular path. All right, so the first thing that we're asked here is A, what is the child's centripetal acceleration? Well, AC is v squared over r, but you see in this problem that we're not given the linear speed, we are given the angular speed. So we're going to use that derivation that we talked about in an earlier lesson, where AC, instead of being v squared over r, is r omega squared, where omega is the angular velocity of the merry-go-round, and therefore the child. So the radius is 2, the angular velocity is 3, 2 times 3 squared is 18 meters per second squared. We now can use this to solve for the minimum force between her feet and the floor. There's only one force keeping her in the circular path. So sigma F equals ma. Is she accelerating? Yes, because she's traveling in a circular path, so we add the subscript c. Fs equals mac. M is 50, AC is previously calculated in part A is 18, and 50 times 18 is 900 newtons. So the friction keeping her in the circular path is 900 newtons. C now wants the coefficient of static friction required to do that. We go ahead and set up our static friction equation, which would be Fs equals mu s Fn. This child is on a horizontal flat surface, so the normal force is equal to her weight. In the previous question B, we solved for the static friction as 900 newtons. Mu s times 50 times 9.8. So mu s would be 900 divided by 50 times 9.8. And we get a mu s value of 1.84. Is this reasonable? Well, a static coefficient, while it's possible to have one that's greater than 1, it is very unlikely that sneakers, her body, clothes, whatever the case may be, and the surface of the merry-go-round would be able to supply that great of a coefficient. So no, our answer is not reasonable. So we understand that she probably would go flying off of this merry-go-round, tangent to the circular path, which would make for another interesting physics problem here, because she goes flying off as a horizontal projectile, and we could calculate her range, time in the air, and things of that nature. Alrighty. If you have any questions on 6 through 8, make sure you ask in class tomorrow. And then tomorrow we'll finish this set of problems by going over a pretty neat civil engineering question in problem number 9.